Hello everyone, I'm Savitha Mary from St.Joseph College of Arts and Science, Cuddalore. In this video, I'm going to explain about a theorem in real analysis. The theorem is first fundamental theorem of calculus. It is one of the main theorem in real analysis. The statement of the theorem is, if f is continuous on the closed bounded interval a comma b, and if f of x equal to integration over a to x f of t dt, then f dash of x equal to f of x. This is the statement. Before getting into the proof, a couple of things mentioned here. First, we have to notice that the given function capital letter f of x is an definite integral over a point a to x. So, a function is given as an definite integral function with another function f of t dt. And the second thing is the implication of the theorem. The implication of the theorem is f dash of x equal to f of x. Here, the name of the theorem, fundamental theorem of calculus, not only the relationship between integration and differentiation, but also it is that any integrable function has an antiderivative. It has given any integrable function has an antiderivative. This is the reason the theorem has the naming fundamental theorem of calculus. Especially any continuous function has an antiderivative. Okay, so now we'll move on to the proof. So to prove this theorem, first we have to know the derivative of the given function. The formula of the derivative of the function is f dash of x equal to limit h tends to 0 f of x plus h minus f of x divided by h. This is the formula for derivative. Okay, so that here I need 2 points x and x plus h. Define the point x in the interval a comma b and also x plus h in the same interval, closed interval a comma b, and here h is strictly not equal to 0. Now define the function f of x plus h as integration over a to x plus h f of t dt. So the function f of x plus h is defined as integration over a to x plus h f of t dt. Now, subtracting these two functions f of x plus h minus f of x, we got the solution integration over x to x plus h minus f of t dt. Because we know that we can change the limits into upper and lower limits by changing the sign. It is a integration of x to a f of t dt. Then combining these two integration, we got the integral like this, x to x plus h f of t dt. So, f of x plus h minus f of x equal to integration x to x plus h f of t dt. And by the given assumption, f is continuous function. F is continuous on the closed bounded interval a comma b. Likewise, the value x and x plus h also taken from the same interval x a comma b. So, it is possible f is also continuous in the interval x comma x plus h, and there are some points which attains a maximum value and minimum value in the interval x comma x plus h. The 2 points I have defined 2 different points, t1 and t2. So when the function takes the value of f of t1, it attains a minimum value m, and f of t2 attains a maximum value capital letter M. And now I have defined an inequality m less than or equal to f of t less than or equal to m. So the function f of t attains a maximum and minimum value. So we can form the inequality m less than or equal to f of t less than or equal to m. Okay. Now taking integration over this inequality, integration over x to x plus h m dt, integration over x to x plus h f of t dt, which is less than integration x to x plus h m dt. And solving this integration of lower and upper end of the inequality, we got m h and a capital letter MH in the upper and lower end, because we know that the integration of x to x plus h m dt will reach the value m into h, because m is a constant value. Integrating the value of dt, we got t, and substituting the limits, upper and lower limits, x plus h minus x will reach. So eliminating the positive and negative values, we got only the value of h for the integral of dt x to x plus a. Okay. So that's why we write the value here, x m h less than or equal to integration of x to x plus h f of t dt, which is less than or equal to capital letter M into h. And now I am going to take this integral, the middle value of the integral, integration x to x plus h f of t dt, as a function of c of h. Here I am defining that particular integral as f of c of h. Why? Because after completing this integration, the integral value can get in some functions of h. So we can define that value as f of c of h. Okay. Here the value c of h is lies in between the interval x to x plus h. In such case, when the value h approaches to 0, the value c of h approaches to x. It is obvious, we can see the value h approaches to 0, c of h will approaches to x. This is the thing I have defined here, limit h tends to 0, c of h equal to x. Then see the f of x plus h minus f of x divided by h is equal to f of c of h, because the right hand side integral value in this equation, this integral will takes the value of f of c of h. Now taking limit h tends to 0 on both sides, the left hand side value will be the derivative, capital letter f dash of x. In the right hand side value, limit h tends to 0 of f of c of h will approaches to f of x, because the value c of h approaches to x. So we got f of x in the right hand side. So finally we reach f dash of x equal to f of x. So we got the antiderivative function for the integral function. This is the thing we wish to prove. So we complete the proof. Thank you for watching this video.